Hi, it's Joe Menchevsky, the host of Better Buildings for Humans. This is a series of conversations with thought leaders about indoor environmental quality. We're going to talk about daylight, views, fresh air, and thermal comfort, and so much more. These conversations are for architects, designers, engineers, building owners, people who care about the comfort, health, and productivity of the people who work, live, and play in their buildings. Come join us if you want to be a part of the conversation. Today I'm speaking with David Geisler-Moroder. David is a mathematician who has turned his expertise towards the world of energy-efficient buildings with a focus on daylight. He's with Leopold Franzen University in Innsbruck, but he's recently worked with Bartenbach in Aldrons and the Solar Energy Research Institute in Singapore. Now, David has contributed significantly to modeling the impacts of a variety of window treatments on daylighting. And honestly, he's made a significant contribution to the world of daylight modeling in general. David is also leading the charge to integrate daylight and thermal models, which is a really important step forward. Anyway, if you care about daylighting, view quality, and balancing between energy efficiency and natural light and views, you really want to listen to this discussion. So, David Geisler-Moroder, it is an absolute pleasure to have you with us today. Thank you very much.
Thank you very much for inviting me for this interview.
Oh, it's our pleasure. It's absolutely wonderful for us to get to speak to the people who are at the leading edge of these important technologies. Let's start by having you introduce yourself to our audience and let them learn a little bit more about who you are and what it is that you do.
What I do? Starting at the beginning, what did I study? I studied mathematics, did my master and PhD in mathematics, technical mathematics. And within my studies, I already dropped into the field of lighting and lighting simulation. With that, I came across a lot of mathematical challenges in lighting technologies, how to calculate reflector lens design, things like that, but also color rendering things. And I really went into the topic of daylight simulation then in the end. So it's really the mathematical concepts behind simulations. After my PhD, I took that and worked for 12 years then at Bartenbach, a lighting design firm, close here to Innsbruck. And now, half a year ago, I moved from Bartenbach here to the university to even more dive into the research again and really get into doing research more and more on these topics. And I think the topics, I don't go into the topics now. We're going to talk about that in the next minutes.
Okay, sounds good. So yeah, let's talk about topics. We're gonna, in terms of where you are right now and the kind of work you're doing, let's say within the last year or so, and that's current to you. Can you tell us what you're working on?
It's primarily really working on daylighting simulation and everything that comes with it. That means it's really on the daylighting simulation tools and the core concepts and algorithms of daylighting simulation, but also how can you introduce like daylighting systems in daylighting simulation software. What does it need to connect daylighting simulation to other simulation, electric lighting, but also HVAC simulation, overall building simulation, to really introduce this daylighting aspect into the world of building simulation.
So full integration of all of the systems, not just daylight in isolation.
Exactly. And this is what so our focus was always and still is for me, is on the daylighting part, doing that, but never forgetting about the whole, the great overall picture. Yeah.
Okay, so it's not as simple as just calculating a solar heat gain coefficient and or solar heat gain number and saying that's all we need to know to calculate the load on the HVAC system.
Exactly. You need way more. So that is what you have in the standard that gives you a single number, and that makes it possible to have that in some in your database to select the system, but to really evaluate what does it do to your building, it's not enough, and it's not sufficient to do it on that level.
Do you look at the impact of solar heat gain in the various locations within the building? Like, is that part of it? Is learning how to balance, given you know, the orientation of the building, time of day, those sorts of things?
Exactly. That orientation in the building, but also also thinking about where in the facade you can put and should arrange your facade setup to balance the requirements to the facade that you have in terms of energy, in terms of view, in terms of glare protection, in terms of everything that goes together with daylighting.
Oh, that's incredible. That's absolutely beautiful. Is there any will there be prescriptive type outcome from that, or is it just creating the models that will allow you as an architect to do the balancing, or allow an architect to do the actual balancing themselves?
It is definitely that these tools will guide you and give you numbers, but it's still on the architect side to interpret it, because the tool can tell you, you can give the boundary conditions to the tool and you can predefine that, but you still need to evaluate as an architect, is it what I want? What is the application that I'm designing for? What is the building intended to be, and which kind of users and people are living or staying in that building.
Wonderful. Love that. Oh, I absolutely love that. All right. So I've got to go straight to something a little controversial right at the very beginning. Tell us
Sure.
which software, which daylight modeling software you think is the most robust, most accurate, the most useful.
In terms of accurate, and this is I love to cite that saying. It's from George Box. You maybe know that all models are wrong, but some of them are useful. And I think this is really important to know, that it's a model, and we need to know what the model can be and can hold, and what we can expect from a model. So it's always important to have it everything in a model that is important to cover what we want to see, and which part of the reality we want to model, and what we want to mimic in our model. So in terms of daylighting, for me, and I think most people and researchers in that area, they are in the same opinion, that radiance is more or less the de facto standard for these kind of daylight simulations. And there's different reasons why it is like that. There's a huge research community behind developing new algorithms, new methods, new tools based on radiance or for radiance, and implementing it there first. Radiance is definitely not easy to use if you just use the vanilla version of radiance as it is, but fortunately it is implemented in many easy to use tools that use it as a calculation kernel, and you can then use these tools quite easily. So
excellent. Okay, no, that's fantastic. I'm going to step back into a broader picture on modeling. What would you say are the biggest shortcomings in the current state of the art for modeling?
I think biggest shortcomings are, it's generally in simulation is always, if you think about, there's this paradigm in simulation, garbage in, garbage out. It's always important, and what I said before, it's to know what the model can really represent, what it really represents, what it holds, and what it doesn't, what it isn't able to predict as well. So it's important to know that there are limitations to every model, and there are limitations to every software. And I think it is important to either be aware of these limitations, or on the other side, if a software provides something to a user, only access on the level where you don't need to dig into that depth. That's what I want to say.
Right. I'm not sure there's an equivalent word for that.
Yeah.
If there is, I can't find it either.
And yeah, but I think that the shortcoming is that it is important to know the shortcomings of the software, but on the other side, it is good that these tools that are available out there, they cover this complexity and do that in a way that the user can easily implement the software, and they like also catch all the or most of the erroneous inputs that you can feed into the software. So that's a good way around.
So user knowledge is where the greatest opportunity for improvement is.
Yeah, that's one thing. The second thing for me is in daylight modeling is the lack of availability of product data to get daylighting systems, facade systems, fenestration systems into daylighting software. This is something where there's really a lack of available data. If we compare it to the electric lighting world, every luminaire, you can, for every luminaire, you can just go to the internet, to the website of the vendor, of the manufacturer, and download an IES file, or in Europe a OILUM.dat file, and just implement that in your software. For daylighting systems, that's way harder, and this is really a barrier, that this kind of data are not available.
Okay. Oh, that's really interesting as well. How easy is it for vendors to create that data, to make that data available?
That's a very good question. There's a lot of work going on in research to come up with easier and faster methods to create this kind of data, because it depends a little bit on the type of system that you have and on the complexity of system, and it may not even be a complexity that you realize as a user or as an architect as a complexity, because one of the maybe from working with it, one of the most simple systems like a fabric shade, it seems to be simple, but that one is one of the hardest systems to be represented in terms of daylighting of system data to be used in daylighting simulation.
Right, the surface of the threads are almost chaos.
Yeah, yeah.
Interesting.
Exactly.
You do some work there, right?
Yeah.
That's some a little beyond my mathematical ability even to grasp it. So that's very cool. Let me change gears a little bit again. I want to talk. Well, this is a nice lead in. You've done work modeling traditional window treatments, blinds, etc. Have you done any research with like light diffusing or redirecting glazings?
Yeah, we also worked with that. In terms of what we just discussed, introducing them in daylighting simulation, blinds are thankful systems. They're easy to model. There's a base material. You can characterize this base material quite simple, in a quite easy way, with either you get available product data of this base material, and then you can just do geometrical modeling of the blinds. If it comes to microstructured systems or even diffusing systems, if they are not ideally Lambertian, so ideally diffuse, what they usually aren't, then it's not that easy, and you really need to get into modeling them properly, or measurements of these kinds of systems, and then it's getting quite complex and quite quite expensive, and also time consuming to really generate this kind of data. And there's a lot of work going on to make it easier to come up with these kind of product data to be implemented in software later.
Who's leading that kind of work? Is that yourself, some contemporaries? Who are the leaders in the field?
There's like, it's a big, not big, it's daylighting. Daylighting is not a big community. Daylighting is a small community. It is a niche, but it's a very important niche. And it's so, and there's definitely in the US, it's Lawrence Berkeley Lab. They are really drivers in that area. In Europe, there's in Switzerland, there are universities doing that. Here in Innsbruck at the university, we're working on these kind of things. And there's this Fraunhofer Institute. So there's some research institutes working on these kind of things, to really getting daylighting system characterization to a next step. Maybe an interesting follow-up reading for people watching this interview. In the finished IA task 61, the solar heating and cooling task 61, we had a lot of these groups together, working together on summarizing what is the current state of the art in these kind of daylighting characterization, and what are possible ways to do that in simulation and in measurement. And there's a lot of publications out there. So for the interested reader, that's maybe a good follow-up here.
Yeah, we've done some work internally on modeling diffusion. And at some point, I'd love to get our people talking to you and to some of your people. I think that would be a brilliant
Sure.
conversation.
Yeah, would be great.
Okay, wonderful. I'll very much put that on the to-do list. I'm going to take you in another very, very different place now. The work you spoke of earlier in terms of integrated simulation, we're bringing all the factors together into one simulation. Is there also an opportunity for integrating AI into that sort of scenario?
Yes, and I think so. There is it's the important thing. It's maybe one step back, and if we talk about daylighting, there's different aspects to daylighting. It is not only the visual part. We talk about daylight provision. We talk about daylight distribution that we need. We have glare protection. We have view to the exterior. They are quite contradictory. So and there's the solar gains that we want to use in winter, or we want to have solar shading in summer, and then there's all these non-visual effects. So it's really a huge bunch of aspects that we need to deal with, and this is, I think, where AI can come into the play to say, okay, looking into that, and we have so many different aspects to consider when designing daylighting and when planning daylighting, that AI can help through huge data models to really come up with suggestions. What is the best way? Usually there's not only a single person sitting in a room, so also getting into these multi-user problems, let's call it problems, but it's multi-user interests in an open plane office, for example. So this is definitely a place where this can come into the play.
Yeah, and ultimately it's still with the architect to interpret the data and make the best human decisions. Okay, let's talk about view. I'm going to change gears completely. I want to talk about view a little bit because I know you're connected to a lot of the folks that are doing that research, quantifying view in terms of view clarity, view content, view access. How does that connect to your research? How do the two complement each other?
I was invited to contribute to a very interesting paper exactly on that topic and all these view aspects. And my part, and this is why I was invited to do that, is that if you design a building, view is one of the aspects that you need to take into account when designing your facade and designing your windows and shading systems. And doing that and designing and planning and simulating view is one of the hardest things, and there's a lot of research going on. It's really a huge topic out there, how to do that properly. Is virtual reality, augmented reality, is this technologies that can help in designing these things. What interested me most in this case was, if we have systems and fenestration systems, blinds, fabrics, diffusing, glazing, whatever, in our facades, how does that contribute to this topic of view, and how can we in advance predict if the view component in this room is then if sufficient, or if it is comfortable for the people in there. So are there ways to simulate the view contribution and the view part in this design that we have? And this is exactly what we were doing here. So getting back to the discussion earlier, we need this kind of product data for systems, but how can we set up this kind of product data in a way that we also have numbers in the end, or in the end, it will be numbers telling you how good view to the outside is.
That is very interesting. It's not intuitive to imagine a quantitative description of view, but it's
in the
brilliant.
end, yeah, and in the end, if you want your building to be LEED certified, and you need to get some credits, you need something that you can judge, and you need to have some numbers where you can say, okay, that one is better and that one is worse.
Yeah, fantastic. Yeah, I love that. Okay, let's talk about energy codes a little bit. Lots of pressure on architects these days to as we have spoken of earlier, to move towards purely opaque buildings with little punched holes in them. Not ideal for sure. We want to maintain views, we want to maintain daylight, we want to maintain the ability to connect building occupants to the outside world. Is any of your research, the things you're working on, provide insights into how we can continue to connect building occupants to the natural world while simultaneously getting really good energy efficient building envelopes?
Yeah, that is definitely, and there's research in different directions going on, either developing and thinking about new kinds of daylighting systems and facade systems that allow to bring together these contradicting requirements to daylighting that we've talked about. That's the one thing, and the other thing is, and this is maybe even more interesting for architects, to say, okay, also thinking about and designing the facade. The facade is one of the most important things the architect can work with. This is like, it's like like what you show to the exterior. So this is what you show from your building to all the world out there. And from this point of view, it's important to think about, okay, let's take a simple example. I can split up my facade into two parts, like take the upper part and the lower part of the facade in every room. And it doesn't matter from an energy point of view if I put a daylight redirecting or transparent system on the upper half or the lower part of the facade, but in terms of daylighting, it really matters. It is a huge difference if you have your transparent part on the floor level, or like the lower part of your facade, and or if the transparent part is the upper part, because it just gets daylighting way further into the depth of the room. But the solar gains that you get through your facade is just the same. So this is something that is really important to think about in designing the facade layout. The other thing in talking about these things, and I think there are really more and more steps going on, and we are doing research a lot here on these kind of things, using intelligent controls for movable and adjustable systems. This is something that is really important, with only just using the same system, but using a different intelligent control and combining the control with the overall building control. It's electric lighting, but also HVAC control that can help so much to reduce energy demand and energy efficiency, and increase energy efficiency of the building in the end.
So I'm guessing that all of the electromechanical building blocks are there. It's just a matter of getting the algorithms for control right. Is that accurate?
Yeah, to get the algorithms right and to bring the trades together. That's a big hurdle in the building industry. Is people are, it's like there's the facade and there's the electrical engineer and there's so they're not working together. They're working on their single parts but not bringing it together. But having a holistic integrative control that can enable so much in terms of energy efficiency.
In North America, we have a saying, it's like herding kittens.
Yeah.
I don't know if you've heard that one before, but it's probably accurate in describing that challenge that you just spoke to.
Yeah.
This has been wonderful. I'm going to ask you one last question, and that is, if you had an unlimited budget, your government or the governments of the world came together and said, David, you can have as much money as you want, do whatever research you'd like to do, what would you work on first?
That's a good question. That's the wrong question to a researcher. There are so many questions we want to solve.
Well, give me three.
But,
I'll give you three then. I said one.
okay,
You can have three.
I would split it into two parts. Maybe
Okay.
the first thing is to spend a lot of time and money on developing a, like, call it Swiss Army knife daylighting system that really can do everything that we want. It provides view, it provides glare protection, it provides solar protection, it provides redirection whenever we need it. So that would be one thing. And the second part, as we talked about that earlier, finding ways and workflows that are easy to use, easy to implement. And I guess, and this is one of the important things, even if I'm in research and should not look on these kind of things, but that is also cheap, to workflows that allow manufacturers to really characterize all of the systems. There are so many systems out there, but it's not possible to use them in the planning, in the design phase at the moment. So getting something out that really every single system on this planet can be used in daylighting software. That would be my dream.
Right. That is brilliant and an absolutely worthwhile dream. I can't thank you enough for making the time to speak with me today, David. That was an incredible experience. You and I will definitely be speaking again in the future, because we've got some mutual interests in terms of the research. So
this conversation was made possible by Advanced Glazings, helping you to make the connection to the outdoor environment through daylight and views. Solera and Solera Wow highly insulating light diffusing glass will help you to create buildings that are stunning and will wow everyone who enters.